So in this video, we're going to talk about some basics about the discrete time signals and systems. So we're primarily interested in discrete time signal processing. So let's talk about some of the fundamental discrete signals and some fundamental operations that we can apply on those discrete time signals. So how to actually represent a discrete time signal in Matlab, right? We talked about Matlab in previous videos, how you can actually represent a discrete time signal in Matlab. So the first thing that you have to sort of think about is that um, you basically need two vectors to represent a signal. One of the vector is just used to indicate the locations of the time samples. It's basically the time axis. So a discrete time signal is still a signal as a function of some horizontal axis, and you need a vector to represent that horizontal axis. And this horizontal axis is basically a vector with the time location. Suppose your signal is a time signal, it's a time series, and then at what time locations or at what time point you're actually taking a sample of that particular signal. So you need to have a vector to represent the locations of the time samples. And the other vector is basically used to represent the amplitude. So the amplitude of the signal, it could be positive, could be negative. For one-dimensional representation of a particular signal, for a scalar signal, for example, all you have is just an amplitude. It could be positive or negative. It could be any kind of value, right? But for a digital signal, it can only be a value that can be represented by a computer, because we are actually doing the processing in Matlab. So a computer can only represent a certain type of real numbers, basically a subset of the real numbers. So so we're basically looking at two vectors, one for the time series for the time axis, and the other for the amplitude. So let's look at one particular uh, example. That's the unit sample sequence. Why do we call it a unit sample sequence? First of all, it has an amplitude of 1 at just the location n equals to 0. And it has an amplitude of 0 at every other location. So here I'm actually using n to represent the horizontal or time axis, the horizontal axis. And then delta n represent the signal as a function of n. So that's probably the simplest signal that we can actually imagine. And how can we actually write a function to represent this particular sequence, right? Um, let's give it a try. And um, the first thing that I'm gonna do is to sort of open the Matlab editor. Um, so here I have my Matlab that's open. So for this particular window, I have just two windows viewable, which is the figure window and then the command window, these two windows. So now let's try to write a function that can represent this unit sample sequence. For this particular function, what we really want is that we want a unit sample sequence that's not exactly centered at n equals to 0. We want to make the location of the unit amplitude to be a variable that the user can actually enter. And we also want a variable range. So here n is not sort of specific to a particular range. So it only specifies that when n equals to 0, delta has a value of 1, and n not equal to 0, it has a value of 0. But in reality, we usually want a sequence that has a finite duration. So we would also like the user to enter the beginning and the end time, or the beginning and the end n of this particular sequence. So let's try to write an impulse function. So in the command window, I can use the edit command to open the editor window. And then I'm gonna give it some file name, impseq. It's gonna be my function name also, impulse sequence. it's telling me that this file doesn't exist. Do I want to create? I say yes. So now it's actually opening an editor with a uh, with a uh, with the correct file name that I just specified. And because I want a function, so I use the keyword function. And then let me try to specify the function name. The function name has to be exactly the same as the file name. So it's going to be impseq. And then it's going to have a output, a set of outputs, and also a set of inputs. So what's going to be the output? What I was telling you is that any kind of signal in Matlab needs two vectors. You can output a matrix with two columns or a matrix with two rows. It doesn't really matter. Or you can just output two vectors. One vector for representing the amplitude, let's just call it x, and then another vector that's representing the horizontal axis, let's call it n. So x is actually the signal amplitude, and n is going to be the horizontal axis, the time sample, equals to the function name and then a set of inputs. Don't forget to enclose the outputs with a pair of square brackets, right? That's sort of the syntax we have talked about. Um, in recent versions of Matlab, there might be some kind of a different requirement for the square bracket. Maybe you can sort of not using it, but I haven't checked. But you might want to sort of take a look. And then let's try to specify the inputs, right? So the first input that we want is an input to specify where you want to put the unit amplitude. Let's just call it n0. N0 is going to be the location where the amplitude is going to be unity. The amplitude of the signal is going to be unity. And then we also want a range. So n actually goes from some value to the other value. So that's going to take two values, two inputs. N1, let's just call it N1 and N2. Right. So basically that's going to be the definition of a function. Right. And now let's try to write the body of the function. The first thing we're going to do is to write let's write a comment line, for example. Let's write two comment lines. Generate xn equals to delta n subtract n0. N1 smaller than or equal to n smaller than or equal to n2 percentage. And then if you want the user to be able to type help and then display and the to type help followed by the function name and then display how to use this particular function, you may want to show user how to actually use this particular function. You can give the user the definition of the function. N0, N1, N2. Basically, it's the definition line without the function keyword. So this way, if the user type help impseq, then it's going to display these two lines. The first line tells the user what's actually the purpose of this function. The second line tells the user how to use this function. So it's going to take three inputs and then generate two outputs, right? So now let's try to write the body of the function. What's going to be the horizontal axis? The horizontal axis is going to be simple. It's just going to be n1 colon n2. We're using a unit sampling interval. So the horizontal axis is going to go from n1 to n2 with a stride that's 1. And then what's going to be the amplitude? Right. I'm going to write the body of the function, and then I'm going to explain what's actually the meaning of this particular line. So inside of this square bracket, I'm actually doing a comparison. I'm actually comparing n subtract n0 with 0. So if n subtract n0 equals to 0, this comparison is going to return true. Otherwise, it's going to return false. And in Matlab, true is actually represented using the number 1, and then false is represented using the number 0. So n subtract n0 is what? Here I constructed n. It's a vector that goes from n0 to n2. And then n0, no, n is actually a vector that goes from n1 to n2. And then n0 is another user input. It's a scalar. It's just a number. You're supposed to have this number that's sort of between n1 and n2 so that you can see the pulse, see the unity pulse. Otherwise, if n0 is beyond, is either smaller than n1 or larger than n2, then this unit impulse is not going to sample, is not going to give you a unit of amplitude within this range. It's just going to give you flat zero, right? So here I'm actually using n, this vector subtract this scalar. So what's going to happen is that every element inside of this element, this vector n, is going to subtract n0. Those and then do this comparison is also carried out element-wise. So if at some value of n subtract n0 returns a 0, then this comparison is going to be true. And then you can just obtain the correct sequence. But let's give it a try. Let's give it a try. So I have saved the function by clicking on this button. So let me just try to call. First, let's try to type help impseq and see what's going to happen. It's displaying these two comment lines that I just wrote, right? And then let's try to sort of, let me just use big X, big N equal to impseq n0. I want my amplitude to be centered at location 1, suppose. And then I want my sequence to go from like -10 to 10. So now I have two vectors. I can plot them. I have a figure, empty figure that's open. I can plot them. But this time, instead of using plot, as we talked about in the Matlab tutorial, we're going to use another function that's called stem. I'm going to do stem nx because it's going to show you what's actually the locations of the time samples actually. So where the location of the time samples are indicated by those circles, and then the length of the stick is going to tell you the amplitude of the signal. So at n equals to 1, you'll get a unity amplitude, and at every other locations you're getting 0. So the amplitude is 0. So that's exactly what we were actually expecting. Right. Matlab has a function that allows you to check the type of some of the data. So now we have two vectors that's in our memory space. We can use the function called class to check what's actually the type. So let's try to look at what's actually the type of n. It's telling me it's double, which means that n is a vector of numerical values. So everything that's inside of the vector, every element inside of this vector is actually a double. So if I do class x, it's going to tell me it's logical. It's not exactly a double, which means that every element inside of this x vector is a logical value. A logical value is either true or false. It's a Boolean value. It can only take two values. So, but that's not exactly what we wanted. We want a x vector that's also a double. So every element inside of the x vector is actually a double. So how can we actually do that kind of type conversion? The conversion can be done by doing a typecast. So what we have to do is to use a function that's called double, and then enclose everything inside of this double function. So that's going to give us a output value that's being converted from logical to double. So let's just save it, and then let's run it again. You can use the up and down arrow key to repeat a previous command. And if you actually typed the first few letters of a particular previous command, then use the up and down arrow key, then it's going to repeat the previous command that starts with the letters that you have typed. So now let's try to check. And the class X actually has changed to a double. And if you want to make another plot st, and they are going to look exactly the same. Doesn't really change the look of this particular function. So now we have a function that allows us to specify a impulse sequence, unit sample sequence. Now let's look at a second type of function. It's called a unit step sequence. And this unit step sequence has a function definition that looks like that. So at n larger than or equal to 0, it has a uniform amplitude of 1. And when n is smaller than 0, it has a uniform amplitude of 0. So it's called a unit step sequence. So now let's try to write a function that can represent this unit step sequence. Again, we would like to specify where the amplitude actually, at what sample point this amplitude actually turns from 0 to 1. We're gonna make this parameter as an input parameter, and the user can specify the location. And then we would like to specify the range of this step sequence. What's actually the range of n? So now let's write another function. Let's call it step seq.m. Step seq.m. So now again, using the keyword function, and then our output, we're gonna have two outputs: the amplitude of the signal and the horizontal axis of the signal equals to step seq. N0 is going to be the sample location where the amplitude turns from 0 to 1, and then the range N1 and N2. Again, I'm going to write two command lines. Generate x n equals to unit step sequence n subtract n0, n1 smaller than or equal to n smaller than or equal to n2. Then how you can actually use this function, x n equals to step seq n0, n1, n2. Now the body of the function. The first thing we're going to do is still try to generate the horizontal axis, right? N goes from n1 with a unit stride goes to n2. And then what's going to be the function, the amplitude of the function, right? So again, we can actually try to use the logical comparisons. So we're going to use n subtract n0, and then we're going to compare it with larger than or equal to 0. So the idea is actually quite similar to the idea that we used when we were writing the impulse sequence, right? We are doing a comparison of a vector with a value, and the vector is basically the horizontal axis subtracted n0. Here I'm actually doing the same thing. So the input vector, the horizontal axis n, is constructed from the two input vectors based from the range n1 and n2. And then I'm subtracting a scalar n0 from n. And here I'm actually getting another vector. So it's basically every element inside of this vector is basically every element inside of n subtract n0. So if at some location inside of n, the value of n actually becomes bigger than n0, then this comparison is going to become true, and true is going to be represented using 1 in Matlab, and otherwise it's going to be 0. So again, I would like to turn it into a double instead of logical. So that's pretty much our function body. Let's save it. And let's give it a try. X1 and 1 equals to step seq. Now maybe I want to make my switch from 0 to unity amplitude has happened to from -1, for example, and then the range goes from -10 to +10. And now let's try to make a plot of it. Let's switch to the figure window. Here it's our impulse plot. Now let's still use stem n1 x1. So that's gonna be our unit step function, unit step sequence. So here's the horizontal axis. Here's 0. So when n equals to -1, the amplitude goes from 0 to 1 and stays at 1 at every location that's larger than -1. And the amplitude is 0 for every location, for every time sample that's less than -1. So -1 is here. It's not marked. It doesn't have a number on it, but you can guess. This is -2. This is 0. So this is -1. Right? That's called a unit step sequence. So you can still try to construct more such functions, right? We also have real valued exponential sequence. A real valued exponential sequence looks like that. Xn equals to a to the nth power. A is some kind of real number. And but instead of writing a function, I'm just gonna type the command inside of the window, inside of the command window. So what I'm gonna do is that I'm just gonna first construct a horizontal axis. For example, n goes from 0 to like 10. I just want 10 samples that goes from 0 to 10. And then I'm gonna construct my amplitude. The value a, I'm gonna just pick an arbitrary number. That's 0.9, I suppose. And then I'm gonna take the power of a to the nth power. But the n is actually a vector. So how do you actually do that, right? How do you actually take the power of a vector? If you do that, you're gonna get something that's not exactly what you wanted, and it might be a syntax error. So if you want to do it element-wise, raising a power by n, and n is actually a vector, you have to use the dot hat. The dot hat is gonna apply the power to 0.9, and that power is gonna be dependent upon the elements inside of n. So the first element inside of x is gonna be 0.9 raised by 0th power. And then the second element in x is going to be 0.9 raised by the power of n, 1. And then the last element inside of x is going to be 0.9 raised by the power of 10. So let's just compute it. Let's just compute it. And then let's try to make a plot of it. So that's going to be the sequence. So the first element is going to be 0.9 zeroth power, which is going to be 1. And then the next one is 0.9 first power, that's 0.9. And then 0.9 second power, that's 0.9 squared. That's about 0.1, 0.81, I think, right? So, and then that's 0.9 tenth power, right? So that's what we call a real valued exponential sequence, right? So if a actually has a value of smaller than 1, you're gonna getting a decay sequence, right? So suppose I change it. X goes from like instead of 0.9, I'm using 1.1, for example, right? And then you can imagine what's going to happen. And the trend is going to keep increasing. So depending upon what's actually the value of a, is it smaller than 1 or bigger than 1, you're going to getting either decay sequence or a increasing sequence. And it's called a real value exponential sequence. If you have learned about complex numbers before, we also have complex valued exponential sequence, right? So here is how you can actually represent a complex valued exponential sequence. Xn equals to e. E is a natural number, and then sigma plus j is sort of the imaginary unit. So this is basically, the number that's in this parenthesis is basically a complex number with a real part and then imaginary part. So this is sort of in a representation that's called a polar representation. if you haven't learned about complex numbers before, we can sort of spend some time to talk about different representations of complex numbers and how you can actually apply operations on them. But for now, let's just uh, uh, accept that this is some representation of a complex number and then raised by nth power, and that complex number is this part of the representation is e to the sigma plus j omega, and then you are raising it by nth power, raising the whole thing by nth power, right? The whole thing that's been selected by nth power, and this n is a vector, right? So let's try to construct it. Let's try to construct again. I'm gonna use the horizontal axis that goes from 0 to 10, right? But now let's try to construct the x equals to what? X equals to exp. Exp is a Matlab intrinsic function, and it can take either real numbers or complex numbers. And sigma plus j omega, I'm gonna give it some complex number that's 2 plus omega. I'm gonna give it some arbitrary value that's 3. And then in Matlab, the unit of the imaginary unit is either I or j. Here I'm gonna use j, but don't put a multiplication sign between 3 and j, because 3j is sort of the imaginary part. Don't put a multiplication sign between them, right? So it's a 2 plus 3j. That's a sigma plus omega j, basically, right? And then I'm gonna sort of multiply this complex number with the vector n. So here I have to use the multiplication n, and I close it. So this is a scalar actually. A complex number is still a scalar. It's not a vector. So it's basically a scalar, the whole thing that's in the parentheses, multiplied with the vector. And then exp, this intrinsic function, is going to be applied element-wise on the resulting vector. A scalar multiply a vector is still a vector, is a vector. So exp applied on a vector is going to be applied component-wise. And this way we're going to get a complex sequence x. So let's try to make a plot of it. Make a plot of this complex sequence. The complex sequence has both the real part and also the imaginary part. But instead of plotting the real part and the imaginary part, we're gonna plot the amplitude of this complex sequence and also the angle, the phase angle of this complex sequence. So I'm gonna make a subplot, and in Matlab the command for making a subplot is just called subplot. And then what I'm gonna do is that I'm gonna split this figure window into two parts, left part and right part. So I want a 1 row and 2 column plot. So 1 row, 2 column plot. And then I'm gonna use the first subplot. So it's 1, 2, 1 row, 2 column. I'm gonna use the first one, 1. So it gives me this sub window. And then let's try to make a stem plot of the absolute value of x. The horizontal axis is still gonna be n. And then what's going to be the vertical axis? The vertical axis is going to be the absolute value of x. We're going to plot just the amplitude of this complex number, right? So ABS means taking the absolute value. So for a real number, the absolute value is going to be always positive or 0, right? And then for complex numbers, the ABS function is going to give you the length of that complex number. A complex number is just like a vector, basically. It has just like a two-dimensional vector, basically. And then a two-dimensional vector has a length. So ABS function allows you to gives you the length of that vector. So now that's the amplitude. That's the amplitude. It increases from a very small number to a very large number. 5 times 10 to the 8th power. It's a very large number, right? Probably just because the real part, the amplitude part of this complex number is quite large. It's actually e to the second power, right? So you can actually factor out the amplitude of x by looking at this particular expression, right? And then let's look at the angle. Let's look at the angle. Now I'm gonna use subplot. Still one row, two column, but I'm gonna use the second subplot, and then it gives me this sub window. And then let's try to make a plot of the angle, of the phase angle, what we call the phase angle. If you think about complex numbers as vectors, the vector has a direction, right? If you are thinking about it as a two-dimensional vector, it has a length, and then it also has a has a direction, and that direction is given by the phase angle. Actually, the angle is sort of a representation of the direction. So here's the length of the vector, but because you have like 10 different vectors, so you have 10 numbers, and so that's the length of each of the 10 numbers. And now let's plot the angle, the direction of each of the 10 numbers, right? Each of the 10 complex numbers. So again, stem n, horizontal axis is going to be n, right? And then there's a function that's called angle x. So again, angle x, angle is the intrinsic function, x is the vector, a vector of complex elements, actually 10 complex elements. So angle x is going to give you a vector that has 10 computes the phase angle of the 10 complex numbers inside of this x vector, right? But this angle is going to give you the angle in terms of radian. It's probably not, it's not in degrees. So if you would like to convert it into degrees, you have sort of to do some manipulation by yourself. The thing that you have to do is to multiply a constant, that's 180 divided by pi. So pi is sort of equivalent to 180 degrees. So this number allows you to actually convert from radian to degrees, right? And then let's just make a plot. And then that's going to give you the phase angle of all the 10 different vectors, the 10 different complex numbers. Right? So how you can actually do a complex valued exponential sequence, right? Another basic signal. Of course, you can also do sinusoidal sequences, like this kind of thing, right? A cosine function with some oscillation frequency, and then a phase, and then an amplitude, and it's just gonna keep oscillating. Um, but instead of just doing like one cosine, um, let's just do something that's slightly more complicated. Um, Let me clear out the window first. But let's try something that's slightly more complicated. I'm gonna construct a sinusoidal sequence that's actually composed of two cosine and sine function, one cosine function and one sine function. So what I'm gonna do is I'm gonna type x equals to 3 times cosine, 0.1 times pi times n. So the oscillation frequency is going to be 0.1 pi, zero point 0.1 times pi, and then times the horizontal axis, right? And then pi divided by 3 is going to be the phase theta. So it's going to be, that's the first signal that I'm going to do. And then I'm going to add a sine function to it. 2 times sine, 0.5 times pi. So it's 0.5 pi times n. And then I'm just going to leave the theta, the phase shift to be 0. And then that's going to be my amplitude. So if I want to make a plot, stem nx, then it's going to look like that. It's kind of quite complicated stuff, right? Quite complicated. Positive, negative amplitudes, and bigger and smaller amplitudes oscillating around 0. So random sequences. Matlab actually has a command that's just called a rand and takes two inputs: the row, the column number. The row is the column number. Suppose I want 10. So it's a one row, 10 column, random vector. And then if I want to do stem in x, no, sorry, it's probably 11, I think. Right? It's a sequence of random numbers, random sticks. Before we talk about the operations that we can apply on those signals, let's look at one more basic sequence. That's called a periodic sequence. A periodic sequence has this kind of characteristics. So basically, the value inside of the x basically repeats itself for every nth big N samples. So xn equals to xn plus big N. And then the smallest number big N, smallest big N, is called the fundamental period. So if you have like a if you take a small n to be, for example, 1, and big N to be the number 10, for example, so x1 is gonna equal to x1 plus 10, x11. So x1 is gonna be x equal to x11, and then x1 is gonna be equal to uh so suppose you pick n equals to 11 now, right? So x11 equal to x11 plus big N still 10, right? 11 plus 10, that's 21. So x11 equals to x21, right? So if the signal actually follows these kind of characteristics, it's called a periodic sequence, right? So here we have a random sequence that has like 10 numbers in it, 10 random numbers in it. It's a vector with one row and then 10 columns, right? Let's try to construct a periodic sequence from this sequence, right? This sequence is not a periodic because it doesn't repeat itself, right? It doesn't repeat itself. So x1 is not equal to any other numbers inside this sequence, right? It's a random sequence, but we can actually make a periodic sequence out of this non-periodic sequence. The simplest way is to use repmat. So suppose x equals to repmat. We're gonna use big X to represent the periodic sequence, and we're gonna repeat the small x vector. We're gonna repeat it like 1 times in the row, but 10 times on the column. So if you look at the size of x, it's gonna be 11 times 10. It's gonna be 110. And then the horizontal axis is gonna be what? The horizontal axis is gonna be, instead of just for now the n has only 11 numbers in it, and n is basically goes from 0 to like 10, right? But now let's try to sort of extend it to like a 0, from like 0 to 110. So let's construct a big N equals to 0 to 110, and then let's make a plot of it, big N, and then big X. Oh, sorry, 109 actually. And you can sort of see the pattern that's actually repeating itself. Maybe repeating it about like 10 times is too many, but you can sort of see the cyclic nature, the kind of cyclic nature of this particular periodic sequence, right? If I repeat it just by like 5 times, for example, big X equals to reprimand, you repeat it by 5 times, and big N goes from 0 to like 54, for example, and then stem. And this is called a periodic sequence. Smallest n is going to be called the fundamental period, and what's going to be the smallest big N for now, for this particular sequence? Smallest big N is going to be what? It's going to be the length of small x actually, 11. So what you can check is that x1 is going to equal to x1 plus 11. 1 plus 11. So the period, let's call it t, big T, is going to be the length of small x. Let's just call it big T, the fundamental period, right? The fundamental period is going to be 11. So x1 plus big T is going to equal to, let's do a comparison, x1. 1 means true, right? So this comparison is true. Right. If I use integer types of if I use an integer times t, it's also gonna work, right? So 2 times big T, the fundamental period, is just 2 periods away from x1, and then it's also gonna be true. So fundamental period is the smallest period, right? But if you actually multiply the fundamental period with the integer, it's also one of the periods, right? The same is true for 3, I think. 3. But this time let's check a different point. Suppose like I'm gonna check 5. 5. It's still gonna be true, right? So that's sort of the characteristics of periodic signals. Right? It repeats itself by a certain after a certain number of samples. So those are some of the basic signals that we have that we are gonna use quite often in our future examples. And let's talk about the signal basic operations that we can apply on those signals. The first thing that we're gonna look at is signal addition. Basically, we can add 2 signals together. Right? In principle, it's actually a quite simple operation, right? You just add the amplitudes of the 2 signals together, right? But in practice, we have to sort of pay some attention to the range of the two signals. The range of these 2 different signals could be different. The horizontal axis of these 2 different signals could be different. So we have to take care of that. So let's try to write a function. That can actually implement this signal addition in a robust way. And let's call our function. Let's call our function sig_add. Let's write another function. Let's call it sig_add. And again, it's gonna be a function, right? And then it's gonna give 2 outputs. Y is gonna be the amplitude of the added sequence, and then n is gonna be the horizontal axis of the added sequence, equal to sig_add. And then it's gonna take 2 input parameters, 2 input sequences. X1 is gonna be the amplitude of the first sequence, and then it's also gonna need a horizontal axis. That's the first sequence, the amplitude and its horizontal axis. And then X2, N2, that's the amplitude and horizontal axis of the second sequence. Again, let's try to write some comment to it. Implements yn equals to x1 n plus x2n. Yn equal to sig_add x1 n1 x2 n2. And then y is going to be the sum sequence over n, which should include both n1 and n2. So what I require is that the n, the output of the horizontal axis of the output sequence, should contain both n1 and n2. So n1 and n2 should be just subsets of n. And then x1, first sequence over n1, x2, that's the second sequence over n2. That's gonna be in my comment lines. Now let's try to write the body of the function. So how do I actually first construct a horizontal axis that contains both n1 and n2, right? It's not too difficult. So first I want to take the minimum value of n1 and also n2 and use that minimum value as the starting point of n. So what am I going to do is to take a minimum value of n1 first. That's going to give me the minimum of n1. That's the starting point of n1 basically. And then I'm also going to take the minimum of n2. So minimum n of n1 is the smallest number inside of n1, and minimum n2 is the smallest number inside of n2. And then I'm going to take the minimum value of both numbers. And then that's going to give me the minimum value of n1 and n2. And my n is going to start with this number. So n is going to start with this number. That's going to be the first number inside of n. Colon. I'm still going to use, I'm going to just use, assume, I'm going to still assume just that the stride is 1 for every sequence. If the stride is not 1, it's some floating point number. For example, if your sampling interval is like 0.02 seconds or something, that kind of thing, that can be easily adapted. That can be easily adapted by just multiplying a constant or something. And in practice, you never have to worry about that. You can just, in your signal processing routine, you can just assume the stride is 1. And any kind of a stride that's floating point numbers or can be easily adapted. You don't really have to change your processing codes at all, actually. Now let's try to find the end. Find the end of the last element of n. The last element of n is going to be the maximum value of the two sequences. So I'm going to take the max of n1 first, and then the max of n2, and then I'm going to take the max of both numbers. So min and max are Matlab functions, or Matlab intrinsic functions that allows you to take the minimum or maximum values of two numbers or a vector of numbers, basically. Right, that's going to be my horizontal axis. That's going to be n. Now, we'll have to sort of the length of n could be longer than n1 or n2. It could be longer than any one of them. But x1, x2, x1 is going to have a length that's equal to n1. x2 is going to have a length that's equal to n2. So basically, we have to extend the amplitudes of x1 and x2 also. So we're going to have to extend the vectors x1 and x2 that represents the amplitudes of the two signals. So how we can do that, right? So y1, we're going to construct a new vector. And this new vector y1 is going to be all zeros. And it's going to have one row and a length of n. So it's going to be a zero vector. And it has a length that's the same as this n vector that we just constructed. And then we're going to construct another vector that's y2. y2 is going to be also a zero vector with the same length as y1 and also the same length as n. But instead of repeating the same command zeros here, I'm just going to assign y1 to y2. So y2 has exactly the same shape as y1. Right. And then I'm going to put x1 inside of y1. But I have to make sure that x1 is put into the right location of y1. Right? The position. We have to make sure that x1 is put into the correct position of y1. How do I actually make sure of that? I'm going to just write the command first. And then I'm going to explain this command later. So inside of this command, I'm doing a find command. I'm using a find command. The find command is another Matlab function that allows you to find the indices of the vectors that satisfy a certain condition. And the condition that we're actually specifying is actually here. That's the condition. And the condition is like what? It's actually two conditions that's composing together with an AND, Matlab AND symbol. so the first condition is what? It's this condition. So n must be larger than or equal to the minimum of n1, basically. And then the second condition is n must be smaller than the maximum of n1. Smaller than or equal to, actually. So smaller than or equal to. And for those n's that's within this particular range, so this comparison has to be true, equals to 1. So this equals to 1 means true. 1 means true in Matlab. For those conditions that to be true, then the y1 is going to have values that's inside of x1. So here I'm actually assigning x1 to a subset of y1. And the subset index is provided by this particular find command. And the condition that the find command actually uses is this sort of composite condition. So n must be larger than or equal to minimum of n1, and n must be smaller than or equal to the maximum of n1. So that's going to be my y1. And you can sort of imagine what's going to be my y2. It's actually similar. N must be larger than or equal to the minimum of n2. And n must be smaller than or equal to max n2. And this condition has to be equal to 1 and equal to x2. Once I have constructed y1 and y2, the output y is going to be relatively simple. Y is going to be just equal to y1 plus y2. And that's going to be my function. Right. So let's give it a try. See if we can actually use this particular function to add two numbers together. Right. So let's construct a first signal. So n1 goes from, for example, -2 to 10. And x1 equals to just the rand size of n1, basically. And then n2 goes from like say 2 to 12, for example. Right, x2 equals to rand size of n2. Right. So if you want to look at these two sequences separately, we can do a stem n1 x1, and I'm gonna use k. K means black. That's the first signal. Right, that's the first signal. And then stem n2 x2. I'm gonna use red. R means red. Oh, so it basically sort of I should have hold on to it. So let me repeat the hold on, and then stem n2 x2. So this way it's gonna plot both sequences together. No. N1 x1 in 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 black, and then hold on, stem n2 x2 in red. Right. So that's the two signals. Black is the first signal, and then red is the second signal. And they have some overlap. For example, from like 2 to like 10, I think, right? But they also have different range. So the black signal actually goes from -2 to 10, but the red signal actually goes from 2 to 12. So, but let's see if we can actually construct a third signal. The x3 n3 equal to sig add, but by just using the function that we have just written. x1 n1 x2 n2. And then let's plot the added signal. No, maybe I just should plot the added signal on top of these two input signals. Let's just do stem n3 x3, but this time using blue, for example, right? That's gonna be our added signal. Added signal. So the added signal actually goes from -2 to 12. Right? It contains the range of the two input signals. And you can sort of see at those locations where there's only a black signal, the sum is gonna be the blue signal is gonna be identical to the black signal. That's why you don't see the black circles for these 4 points, because the blue circle and black circle overlap each other, so you don't see the black circle anymore. The blue circles are on top of the black circles, right? And then also you have locations where you only have the red signal but doesn't have the black signal, and at these 2 points the blue signal should have exactly the same amplitude as the red signal, and you don't see the red circles because the blue circles are right on top of the red circles. And at those other locations where the two black and red signals overlap each other, the blue signal is going to be the sum of those two signals, right? So it looks like our sig add actually works quite well. And Matlab actually gives you this capability to make improvements on certain functions, right? So here it's actually suggesting me to make changes to the function so that it can improve the performance. So in fact, I don't really have to explicitly call this find function. All I have to do is the find function is basically give you the indices of a particular vector that satisfies those conditions, right? But I don't have to call it explicitly. I can just remove this find call. And then I can just use the condition itself as my indices actually. So I don't really have to compare with 1 at all. I can just use this comparison, use those conditions as my indices, right? And then it's gonna give me the correct behavior also. And let's give it a try, right? Let's still use the same kind of function call, but with this modified function now. So x3 n3 should still look exactly the same. So let me plot on top of it. But this time change to a different color, maybe not blue, but let's use green. Now the green is exactly the same as the blue signal, so you don't see the blue signal at all now, right? So it means that this particular function works just like before, right? So that's one slight improvement of efficiency that was suggested by Matlab itself, right? We can also write a similar code that does signal multiplication, right? So this is addition, adding two signals together. We can also try to multiply two signals together, right? Multiply these two signals together. It's basically an element-wise multiplication, right? In principle, if the range of these two signals are exactly the same, then all you have to do is to do a dot multiply of the signal amplitudes, the two signal amplitudes, a dot multiply. But so let's write a function that's called sig mult dot m. Yes. So again, function, and then the output signal y and n equals to sig mult x1 n1 x2 n2. Let's just write a simple comment. Implement yn equals to x1n times x2n, right? And the syntax, the body of the function is going to be quite similar to sig add actually. So what I'm going to do, I'm going to just sort of copy over some of the lines from sig add, I'm just copy these three lines. Actually, all those lines. Copy it and then paste it. Right. And then the last line is going to be different. So y, the output is going to equal to y1 dot multiply y2. Again, y1 is just a container of x1, but with a length with the horizontal axis that's extended to include both n1 and n2. And y2 is just a container of x2, but with the range extended to include both n1 and n2. Now y1 and y2 all have the same range as n. And at this point you can just do a dot multiply, an element-wise multiplication, then that's it. So let's save it. That's going to be our multiplication operation. It's basically the signal multiplication operation, element-wise signal multiplication operation. So let's again come back to the figure and let's try it out. Right. So let me clear out this figure, right? And then stem. So now x3 n3 is gonna be not sig add anymore, but sig out. And now let's make a plot of it. So stem n1 x1 k in black. Hold on, stem n2 x2 in red, and then stem n3 x3. This time it's gonna be in blue. So n3 x3 is gonna be the multiplication of these two signals. So blue is gonna be the multiplication. Black and red are the two input signals. So for the first 4 points, we have black signal that has non-zero amplitudes, but the red input signal has exactly 0 amplitudes, so the multiplication is going to be exactly 0. So you see that the blue circles are all at 0 amplitudes. And then for the last 2 points, we only have non-zero amplitudes for the red signal and 0 amplitudes for the black signal. So the multiplication is going to be exactly 0. So that's the multiplication of two signals. And for those points, for those locations where you have both black and red, the blue is going to be just the multiplication of these two. So let's go back to this particular function, right? And that's maybe we can add a few more comment lines to tell people how to use it, right? Yn equals to sigma out x1 n1 x2 n2, right? Basically just tell people how to use it. So now we have a function that actually does the signal multiplication. And we also have some other basic operations. For example, scaling. It's basically just multiplying the amplitude of the input signal by a certain scalar, alpha. Alpha could be a complex number, right? A complex number is also a scalar. You can just multiply alpha with that vector, right? And then you basically apply this scalar multiplication on every element of the vector, right? It's an element-wise multiplication with a scalar. And then for the scaling operation is relatively simple, so we are not going to write a particular function for it, right? But in any case, if you want to multiply a scalar, then you can just in Matlab you can just do a scalar multiply a vector. That's it. There's no particular operations to it. And then there's the shifting operation. Shifting operation is so you would like your input signal is xn, but you would like to shift the entire signal to a different location, to a different position. For example, you want to shift it by a certain amount, that's k. So the output signal is going to be the input signal xn that's shifted by a certain amount of k. And the basic property of the shifting operation is that if you actually shift it back, if you shift the output signal back by the exact same amount, you should be able to recover the input signal, right? That's called the shifting operation. And let's try to write a function for the shifting operation, and then we're going to do another operation that's called folding. Basically just flip over the function, so n becomes minus n, and then we're going to talk about something that's slightly more interesting. Now let's write a function for the shifting operation. And as you can see from the expression, the shifting operation doesn't involve changing the shape of the signal itself, changing the amplitude of the signal itself. It only involves changing the horizontal axis, basically. So let's write a function. Let's call it sig shift. And for this function, it's gonna have an output signal with its horizontal axis. That's yn equals to sig shift. And then we're gonna need a input signal and also the amount of the shift that we want to apply. So the input signal, let's just call it x, and its horizontal axis m. So x and m, basically the input amplitude and the horizontal axis for that, the time axis of that x signal. And then the amount of the shift, let's just call it k. Implement yn equals to x and subtract k. So what's going to be our the function body, right? So let's still try to construct the horizontal axis first, n for the output. So what's going to be our output? So n is going to equal to m plus k, m plus k. And then y, the output is going to be y equals to k, y equals to x, the input signal. And then that's it. That's the body of the function. All right. So let's give it a try. We're going to just use x signal that equals to a random signal, one row, 3 columns, and m equals to 0 to 2. So that's going to be our input signal. Stem mx. So that's going to be our input signal with just 3 sticks. And let's try to put it into the sig shift function. Let's call it y n equals to sig shift xm. And suppose I would like to shift it by 5, suppose. And then let's hold on to the old plot and then stem my, but let's use red. So this is the original signal and this is the shifted signal. And if you put a positive number as the input, as the shift amount, then the entire signal is going to be shifted to the right. So it's going to basically delay. So if you consider the horizontal axis to be time, then a positive amount of shift is going to delay the input signal by the amount that you entered as input 5, for example here. Now suppose I want to shift it to the left. I want to advance it. I want my signal to arrive earlier. So what I can do is to y1 n1 equals to sig shift xm, and now I can give it a negative number. Suppose I want to shift it backwards to the left by amount of 3. So suppose I can put a minus 3 here, right? And then if I do stem n1 x1, let's now use black. Now that's the same signal shifted backwards to the left by 3. So that's the beginning of the input signal, which is at 0, and then the beginning of the shifted signal, which is minus 3. And you can sort of see what's actually the sig shift function, right? Now let's look at folding. Again, the folding involves just reverse the sign of the horizontal axis, and it doesn't involve changing the shape or amplitude of the input signal. But we have to be careful. We have to be careful about when we try to write a function for folding, because again, some bookkeeping, some additional operations are needed before we can actually make sure that the function is robust enough. So now let's write another function. Let's call it sigfold. Sigfold.m. Now function, the output signal yn equals to sigfold, and then the input signal xn. So now let me write a comment line. Implement yn equals to x minus n. So this is different from yn equals to minus xn, right? Minus xn means that you're reversing the sign of the amplitude of the signal. So it's gonna, this yn equals to x minus n. I'm gonna show you what's actually the effect after I finish writing the function. The fold function is different from sort of multiplying the original signal with -1. Multiplying with the signal with -1 is equivalent to scaling actually, but you are scaling it with a negative number, so you get the opposite amplitude. But this is actually reversing the horizontal axis. So let's try to write this function. The thing that we have to pay attention to is that whether x is a row vector or is it a column vector. It depends upon the shape of the input function, actually, the input signal. So let's try to find out the size of the input signal by using a size function. So here the size is a Matlab intrinsic function. I'm using the size to take out the row and the column of the input signal x, right? So if c equals to 1, so I'm comparing c with 1, so is a column number equals to 1. So if it is just a one column, then it's a column vector with multiple rows, but it's a column vector. Then y is going to equal to flip up down x. Flip up down is it is an intrinsic Matlab function. That's basically just to reverse the elements inside of a column vector. So the last element in the vector is going to become the first element. And if it is a column vector, you use flip up and down to reverse the element's order inside of that vector. Then else, so c equals to 1 means that it's a column vector. Else means that it's not a column vector. If it's not a column vector, then we're going to assume it's a row vector. A row vector, you also have a particular Matlab function that's called y flip left right. So for a row vector, if you want to reverse the order of every element inside of that x vector, you use flip left to right, LR, to reverse the order of the elements inside of that vector. And then you do AND. So basically that's the output amplitudes. And then we'll have to sort of worry about the horizontal axis. The horizontal axis, it's a little bit tricky. Again, we need to find out the size, the rows and columns of the n, the horizontal axis of the input vector. And if c equals to 1, so which means that n is a column vector. N is a column vector. N is a column vector, which means that I have to use I think I made a mistake here, because the output and the input are all n, right? So that might not be a good habit. Let's just change the input horizontal axis to m. Let's use a different and then here change it to m. So that's the horizontal axis of the input signal, m. So n is going to equal to what? It's going to equal to, because it's a column vector, so if I want to flip it, then it's a flip up and down m. Right? But don't forget, what you're actually implementing is yn equals to x minus n. So you have to put a minus sign in front of the flip up and down. So after you have flipped the ordering of the elements, you need to sort of reverse the sign. Otherwise, it means that it's a row vector. So n equals to minus flip left to right m, and that's going to be our sigfold function. And again, Matlab is actually telling me something here, because the R value is not used. The R value here is not used. Here I'm just using the column, the C value. So Matlab is actually suggesting that I change this to the wiggle. A wiggle means it's an unused output parameter. So I can just change it to wiggle. Now that's the sigfold. Let's go back to the figure window. Let me clean up the figure, and then let me generate another function. So x equals to rand, one row, 3 columns, and then n goes from like let's say 5 to 7, suppose. Then if I do a stem n x, that's the 3 elements of x, and the horizontal axis actually goes from 5, 6, 7, 5 to 7. Now if I do sigfold on this particular signal, the horizontal axis is going to go from -7 to -5, and the signal amplitude is going to be the mirror image of the signal amplitudes that's being shown here. So if I do y y1 n1 equals to sigfold xm xn. Then if I hold on to the old plot and then do a new stem n1 y1, but with red, you guys will see. So this folded image is exactly this. It's a sort of it's exactly the mirror image of the input signal with the symmetry axis that's at location 0. So this is location 0. That's here, and then that's the mirror image. That's the effect of folding. It's called a sigfolding, signal fold. And it's actually a different signal. It's actually a different signal from what? From multiplying the amplitude of the input signal by -1, for example. So if I do y1, so y2 if equals to -1 times x, for example. Here I'm actually multiplying -1 to x, and then hold on to it. Hold on to the figure, and then stem n1 y2. Let's use black. Maybe that's not a very good illustration, because I'm supposed to plot this signal at the location of the input signal. Suppose because you're not really changing the horizontal axis of the input signal by multiplying -1 to the signal itself, right? So what I'm supposed to do is to do ny2, actually ny2. It's supposed to be here. So let me remake this figure. Let me turn off the hold, and then stem nx, that's the input signal. Hold on to it. Stem n1 y1, that's the folded signal, right? And then stem n y2, that's the input signal multiplied -1. So here it's 0 amplitude. This black line is 0 amplitude. So this is the folded signal, and this black signal is actually the original input signal multiplied with -1. The amplitude is sort of reversed, but it's not folded. It's a different kind of operation. as you can see. And the symmetry axis is different, right? For the folding operation, the symmetry axis is n equals to 0. That's the horizontal axis equal to 0. And for multiplying -1 on amplitudes, the symmetry axis is uh, amplitude equals to 0. That's y equals to 0, right? The symmetry axis is this one, is this axis. So different operations, and we have to sort of pay attention to these kind of different operations. Simple summation. If you just want to get a sum of all the amplitudes inside the signal, you can basically just use a Matlab function that's called sum. So I have x, right? If I do sum x, it's going to return the summation of the three elements inside of x. The three elements inside of x, if you sum them together, it's going to give you the... If you just want to do a partial summation, sum x 2 to n, for example, that's going to give you a partial summation. So that's another basic operation, just doing a summation, right? And if you want to sort of multiply all the elements together, if you want to multiply all the elements together inside a vector, you can use the PROD product function inside of Matlab. So if you do PROD function x, and then it's going to multiply the three elements inside of x together. If you don't believe me, it's x1 times x2 times x3, right? It's exactly the same. So PROD, this PROD function allows you to multiply all the elements inside of a vector, inside of a signal together. Sometimes you would like to compute the energy of a signal. What exactly is the energy? Here's the definition of the energy. Basically, you are taking the square of every element inside the signal and then sum them together. So a MATLAB command for getting the signal of energy, you do a summation on the absolute value taking the square. The reason that you have to apply an ABS, taking the absolute value, is because sometimes the signals, the elements inside the signals, are complex numbers. If that's the case, taking the ABS means that you are taking the length of a complex number. A complex number is a vector, basically. So if you are taking the length of that vector, then it will give you the Matlab function for doing that is ABS, taking the absolute value. So suppose I have here I have the x signal here. So if I do ABS x, because all my numbers are positive inside of x, so if I change x1 to minus x1, for example, right? So the first element has a negative sign. If I do ABS x, it's gonna return all positive numbers, right? And if I want to take a component-wise square, I do a dot hat square. That's for applying the power to every element of the x signal of the input signal, and the input signal is the absolute value of x, right? And then you can do a sum. So that's going to be the energy of the x signal, right? And if x actually has complex numbers in it, suppose x2 equals to x2 plus, say, 3j. Now x actually has complex number in it. The first one is still real because the imaginary part is sort of 0. The second one is complex because real part is non-zero and then imaginary part is non-zero. The last one is also real because the imaginary part is 0. And if you still want to compute the energy of the input signal, you can still use the exactly same command, except that the ABS function is going to take the length of this particular complex number, the second element in it, right? And then it's going to give you sort of the energy of this new complex sequence, right? And that's for energy, but how about the power, right? Do you want to get the power? So the power is basically the energy divided by the length of the sequence. The average power of a periodic signal with fundamental period that's big N. So all you have to do is to sum up the energy to get the energy of N consecutive points in your periodic signal. N consecutive, big N, this many consecutive points in your signal, get the energy of it, and then divide by N, and then that's your power. That's power. All right, that's the definition of the power. So in the next video we're going to talk about some useful results based on those operations, and we can see how those fundamental signals like the delta impulse sequence uh, can play a big role when we talk about convolution and systems, that kind of thing.